let's get started. So, welcome to our workshop, Introduction to Protokit. Today, we'll be talking about how you can start building privacy-enabled blockchains using a TypeScript zkDSL. For those of you who don't follow us yet on Twitter, you can see the handle at the very start of the slide. You can also join our Discord server to keep up with the development work, or just head over to our website to learn more about Protokit. This workshop is going to take roughly 1 hour to complete. We have around 30 slides of various content and chapters, and we also have a live coding session at the end, using all the knowledge that we have obtained through the workshop. Plus, I'll stop every now and then to give you room to ask questions. So please leave your questions in the chat. I'll let Rafael collect, let's say, the most important ones, and we'll stop every now and then to answer these. So let's get started with the first chapter. The first chapter is called From Zero to ZK Hero, and it will contain all the basics that you might need to start building zero-knowledge applications. So the first question is, what is a ZK proof, right? ZK proof is a mathematical proof of computation using inputs, public or private, that results in a publicly available output. So it might include a public output too, we just said that. And what kind of computation can you mathematically prove? So it could be various sorts of computation. You can prove that you have verified a signature using the correct public key. You could do a Merkle tree proof or a Merkle tree inclusion, and many more other kinds of computations. You can do like addition, multiplication, and a bunch of other stuff within a ZK proof. So to compute a proof, you first need to start with a proof system. The proof system that we are using in everything that we build is called Kimchi, and it's the same proof system that powers the Mina's L1. To obtain a proof, you first need to execute something that we call a circuit. And a circuit is basically a set of constraints, or is basically the code that you are using, which will be used to create the proof. So like if you want to do your addition, you will write your code inside of a circuit. And once you run your code or run your circuit, you will be given a proof by the proof system. So executing the circuit to receive a proof is one thing. But before you can do that, you have to compile the circuit to get two kinds of artifacts. So you need a prover key to be able to run the circuit and generate proofs. And you also need a verifier key or a verification key, which will allow you to verify proofs. One important thing to mention here is that proving takes much longer than verifying. So once you run an expensive computation within your circuit, you can verify it very quickly and very cheaply. So yeah, that's what we just said. So what's the zero-knowledge part of proving something, of proving some computation? It's the private inputs. So the proof does not contain, in any publicly accessible form, the private inputs that were used as an input into your, let's say, calculation or into your circuit function. So that allows you to prove that you have done a computation on top of a private input that is forgotten and never exported, and that resulted into a certain public output. You can learn more either by like Googling stuff about zero-knowledge proofs. So there's a Wikipedia link, and there's also a link for something called the Mina book, where you can learn more about the proof system itself. To write circuits, you first need some form of like a proof system language. What we use is a library called O1.js. O1.js is effectively a zkDSL for writing circuits. And the code snippet that you see right now is basically a snippet that shows you how to write a very simple counter circuit. So first, you have to install O1.js. Then you have to import the experimental namespace. And on the experimental namespace, you will find something called the ZK program. And the ZK program allows you to define a circuit. So our circuit is going to be called counter. So we'll just save it in a variable. And let's go through the structure of the circuit or the program. So every ZK program has a public input and a public output. You can omit both of these. You don't actually have to use them, but both of them are super valuable when constructing a circuit. So apart from public inputs and outputs, every program can have multiple different methods. And our program only has one method called an increment, which will be used to increment the counter that we will work with. Every method can additionally also have different private inputs. These are the inputs that will not be publicly available as part of the proof. And our increment method contains two private inputs. So let's talk a bit more about what does the circuit actually do. So the circuit inputs and outputs a field. A field is the most primitive or the simplest type of the kimchi proof system. It's 256 bits large, and it allows us to store multiple different types of data, like for example hashes, right? So the built-in hashing library, once you create a hash, it results into a single field. So what do we want to achieve with this circuit? So we want to write a circuit that allows someone to store a hidden number or like a hash of a number, and it allows you to increment the number only if you can guess the pre-image of the hash of that original number. So let's go through the code to make it more obvious. The public input would be the hash of the number that is the current state. So let's say it's 0, so that would be the hash of 0. Then we would have A and B, A being the real value of the secret that you're providing as a private input, attesting to the fact that you actually know the value. And B would be the value by which you want to increment the number within the circuit, prove that you have incremented the number by the given number B. And as an output, we would have another field, which would be the hash of the new incremented number. So this would create basically like a state machine where we can go from one secret number to another secret number in a proven way using a zero-knowledge proof and a circuit. So going line by line through the circuit, we have this increment method, we have these inputs, the public input and the private inputs. The first thing that happens is that we have to verify if the user has provided the correct number as a private input. So if the original state is 0, we would have to first turn it into fields and hash it to get the hash. Then we would have to assert that the hash calculated from the provided private input matches the public input, which means that the user actually knows the number that he needs to guess. Then we will increment the provided number and return back a hash of the incremented number. So let's just move to the next slide where I will show you how this program can be executed and how it can be used to prove state transitions from one number to another. So to run the circuit, we first have to compile it. We already discussed prover and verifier keys. So that's the easy part. Then we define the initial state, which would be a uint64 using the O1JS SDK, and that would be 0. The public input, the starting one, or the initial state, would be the hash of the state. And the number we want to increment by is going to be 1. And then we just have to run the counter contract, or not the contract, sorry, just the counter program. So counter.increment, we provide the public input, so the state that we want to transition from. Then we provide the state in the unhashed format, which is just 0, and then the number that we want to increment by. By awaiting for the proof system to create a proof of the execution of this increment method, we receive a proof of increment, or just a proof. The proof will contain then the public output, which will be the hash of the state plus by, which in our case is 1. So if we started at 0, the increment at 1, the public output of running that function and the public output of the proof would be the hash of 1, because 0 plus 1 and then a hash. So after we run that, we can extract the new public input or the new state from the proof and also update the state because we have just moved by 1. Now the important part is that after you run this computation here, you can very cheaply verify it using the verification key. So counter.verify with the provided proof of increment will verify as valid. So it's like the simple round trip of how to write the circuit to be able to obtain a proof of some computation on inputs and outputs, and then how to verify the proof. So moving on. Another important thing here is that circuits or methods or proofs can be recursive, because verification of a proof is just another computation that can be proven, right? So if you look at the original counter circuit, which had the increment or the add method, we can add another private input, which would be another proof from a different ZK program that can be verified within the counter ZK program. So that could mean that in order to increment the counter, not only you would have to know the original number that the counter is at, but you would also have to provide, let's say, a credential proof that would attest that you are eligible to even modify the counter or to provide a proof of a valid state transition. So recursive proofs are probably the single most powerful primitive in the whole stack. So we'll be working with them throughout the workshop pretty extensively. So how is this helpful for blockchains? Like, what kind of benefits do we have if we try to architect blockchains using zero-knowledge proofs? So we know that blockchain is basically just like a distributed database with a consensus, and it's like a transactional database in effect. So how does a traditional like round trip for a transaction look like? So users sign transactions which authorize their intent to like perform a certain action on the chain, and then nodes or block producers execute these transactions to change the state on the chain itself. These transactions are then bundled into a block, executed. You have state transitions coming out of them, and then you have the new state of the chain after the block has been produced. If you want to verify the block, you have to rerun all of the transactions. This is the case for basically any non-recursive proof blockchain that is out there. Okay, so what does this mean for the network itself? It means that anyone who wants to run a node needs to meet certain relatively high hardware requirements in order to be able to verify blocks. This makes it more and more difficult to decentralize the chain, since the entry barrier is pretty high for people to run nodes. With Mina, the case is, however, quite a bit different. What Mina does, it turns the whole block creation process into a huge zero-knowledge circuit, or actually multiple different zero-knowledge circuits. And these block proofs are then recursively composed to basically. So what this means is that since all of the block production is a series of recursive circuits, it means that the barrier of entry for running a node gets lower and lower, because to verify a block, you don't have to re-execute the transactions again. You can just verify the proof provided by the block producer that with like certainty pretty much tells you that the transactions have been included correctly and that the block is valid. So you don't have to re-execute transactions again. You just have to verify a Mina block proof and a consensus proof and probably a bunch of other proofs, and you have then the latest state. So yeah, block is now a single recursive proof, which is really amazing for multiple reasons. All right, so you can find more information in the Mina protocol architecture. I'll share the slides afterwards so you can find all the links. Let's talk about how do smart contracts work on the Mina's native L1. So we already know that the L1 itself is basically like a huge recursive set of proofs. So to verify the latest state, you just need a single proof. Now, let's take a look at how does it affect the smart contract design and what can you do with the L1 smart contract. So smart contracts on Mina are built using the same O1.js library as the ZK programs that we have seen before. There's a smart contract class that you can use, and people often refer to these as ZK apps. Smart contract is effectively just, again, another circuit that can produce a proof of its own execution. It is executed not on chain like you would normally have like in an EVM model, but instead it is executed off chain, since we can then verify the proof of its execution on the chain without having to execute it again. So before I've said that originally transactions would be assigned intent that would tell the node that the user is trying to execute, let's say, a smart contract method. Here it's different. The user executes the smart contract themselves in their browser off chain and send the proof of execution to the chain itself. Okay, so since the node now doesn't know which code to execute on behalf of the user, it is sufficient that the node only receives a list of called so-called like account updates, which are effectively the state transitions for the chain. And these come authorized by the proof of the execution of the smart contract. So you execute the smart contract, you generate the proof that you have executed it correctly, and that execution results into account updates or state transitions, and these are authorized by the proofs and then sent to the chain to be applied to the chain state. All right. They can also be authorized by signature, so not just the proof. The block producer or the chain then verifies the proofs and updates the chain state. We just discussed that. And all of this is then recursively bundled into a single block proof. So out of all of these recursive proofs, you end up with a single block proof, and you can carry on with your day. So it's really amazing. However, there are also like downsides to this approach. So running all the computation on the clients effectively results into race conditions because these clients are not aware of each other and they have no way of organizing of the chain. So let's take a look at how you would implement a smart contract using O1.js. So the example we're using is the same as the one that we have used for the ZK program, but this time it's going to be a smart contract, and the public input that we have used before is going to be saved on chain as part of the smart contract logic. So we define a class called counter. It extends the smart contract class. Then we have to define some storage that will be stored on chain. Keep in mind that you can only store 8 times 256 bits of storage, which means 8 fields worth of storage. So this contract is only using 1. So for this example, it's completely fine and will work just okay. So what we are storing on the chain using this decorator and this public variable or the public property of the class, we call it commitment, and it's just going to store a single field. Then we will have an increment method that will accept 2 private inputs, A and B, same as the ZK program. The state that is stored on chain will become the public input into our smart contract. The business logic is identical to the ZK program. So we first hash the input that you are supposed to know. Then we fetch the on-chain state and create something called a precondition, which we will explain later. And then we make sure that the calculated hash matches the on-chain commitment. If it doesn't, we throw an error which prevents the proof from being created. Then we increment the numbers again, A plus B, and we create an incremented commitment, and we update the on-chain state with the incremented commitment. So I want to talk a bit more about preconditions and what exactly do they mean. So when your smart contract runs off-chain in your browser on your client, it has to fetch the on-chain state, and then the proof that is created from calling the increment method has to carry public input or output, doesn't matter in this case, basically telling the chain when it goes to verify the proof which on-chain state you have used for your transaction. So when then there's 2 users creating the same proof using the same on-chain state, one of their transactions gets in first, it will invalidate the second proof because both of these proofs were based on the same initial state, which is no longer valid. So that is a precondition. It is an additional validation for your off-chain proof. So let's see how we would run this smart contract. So you would just create a new instance pointing to an address of the deployed contract. Then you would do a Mina transaction by calling counter.increment with the number. One parameter is missing here, doesn't matter. And this call would then create a series of account updates, as we have discussed before. And this will be authorized by a proof. We'll create a state update that will change the commitment to the incremented commitment. And we'll also have the original commitment that we have used in the computation as a precondition. And it will tell the chain that this account update is meant for the address of our smart contract. So when the chain goes to process that address, it knows the verification key of our circuit of the smart contract and can verify the authorization of the account update and apply all of the things listed in the account update to the chain state. So you have to prove the transaction. That is where the authorization of the proof is added to the account updates. And then you, of course, have to send it to the node. So that's like the TLDR on like ZK programs and smart contracts. And let's take a brief look at a diagram of like a life cycle of a transaction on a smart contract. So we start the life cycle by Alice executing the smart contract in the transaction API. She provides the parameters needed for the contract execution. The contract produces a list of account updates. Then it authorizes them by proving the counter.increment method within the proof system, and then sends the transaction to the chain. So, and when the chain eventually goes to produce a block with this transaction and many others, it will do the following. So it starts at the initial chain state where the commitment was, commitment A. Then it goes to apply the account updates. It checks if the account updates are authorized by verifying the proofs associated with the circuit of the smart contract. Then, if the proof is not valid, it throws away the account updates and the transaction is reverted. If the proof is valid, it proceeds with checking the preconditions. So it checks if the precondition, the fact that we have used the initial commitment value to calculate this proof, matches the on-chain state. So if the initial state matches the commitment we have used to calculate the proof, then the precondition will be considered valid, and then the state updates will be applied, and we will end up at the resulting state. So in our case, we go from commitment A to commitment B by proving that the smart contract is really meant to create this kind of a state transition, and then the chain applying that state transition to the on-chain state. Okay, let's talk about key value storage in smart contracts. So far, we've only seen a state that stores a single field. We can use 8 of those, but this is essentially not enough if you want to have a more complex application that stores, like, let's say, user deposits in a key value storage. So the following syntax is not possible with the L1 smart contracts. You cannot just define a key and a value type and then just store multiple values on the chain itself. This is due to like multiple reasons. Like probably the main reason is that every circuit calculation or computation has to be fixed size. So users cannot just arbitrarily define any storage shapes that they want, right? So yeah, so this is not possible. So what can we do about it? Like, how can we build apps that have more states than possible out of the box? So instead of storing like a key value map on chain, we can store a single commitment to a root hash of a Merkle tree, which fits into a single field. That would look like this. So let's explain a bit more about what a Merkle tree is. So, yeah, here we go, wrong slide. So what is a Merkle tree? So Merkle tree is a data structure that allows us to cryptographically verify that a certain leaf is part of the entire structure. So imagine that you have a huge database full of key value records, and you want to do some computation on top of a single row in the database. So the row, in this case, would be the leaf. And to verify the integrity of the data, that the leaf is really part of the database of your table or of your tree, you have to do what is called the Merkle proof, which means going from this leaf and calculating the root through cryptographic hashing to ensure that the data that you are using is really part of that tree structure. And the root is the commitment that we are storing on the chain. So yeah, let's move on. The simplest way to use Merkle trees, in my opinion, is what's called the Merkle map. It's an API provided by O1.js. So all Merkle tree leaves can be identified by an index. If you use a Merkle tree with a sufficient depth of 256, it means that there's going to be 2 to the power of 256 leaves, which is like a lot. I mean, by saying a lot, I really mean a lot, like it's a huge number of all the records that you can have in your key value storage. So thanks to the depth of the tree, it means that the size of the index or the amount of the leaves will be from 0 to 2 to the power of 256. And this means that the index can be represented by a field, because field has the same like range of values pretty much in binary. So this allows us to treat the tree like a key value storage, where the key can be a field, the value can be a field, and the root will also be a field. And that's the Merkle map. So here's how you can use the Merkle map. So first, you have to create a new instance of the Merkle map, then define a key and a value, which both have to be fields. You can take any data type in Snarky.js and turn it into an array of fields, which will then allow you to hash that, and you will arrive at a single field. So we do that for both of our key and the value, and we can then set that to the Merkle map. So the Merkle map will now be a tree of hashes of our values, which we'll be able to find by an index or a key. To prove that a certain value and a key are part of the tree, we have to do it through a witness. So we can get a Merkle map witness, and then using the real value that's supposed to be stored under that index, we can calculate the root hash. So if you remember, going back to here, by providing the value at the leaf, you and receiving this value and this value, you can then compute the first green node, and then using this node and this node, you can then compute the root, which tells you that you are using the correct value for the leaf. So going back to here, computed root and then computed key, which we can then use for our proving. So let's try to write a smart contract that uses a Merkle map based storage for storing user counters, right? So we want to have a contract which allows us to store a counter for a specific public key and then increment it as we see fit. So we define a counters commitment. This is a on-chain state field that will store the root hash of our counters Merkle tree or a Merkle map, and a single increment method that tells us for which public key we want to increment and by what value, keeping in mind that those are like private inputs again. So first we have to do the precondition dance, where we get the state and then we assert that it equals the on-chain state. That's called the precondition. Then we have to turn these data types into something Merkle map compatible. So we have to turn them to single fields. We have this helper that I've just used here, but it does the hashing that we've seen before. So the key for the public key would be a hash of the public key. Then we want to get the current counter for the user, and we do that for the specific key of which is the public key, and that gives us again another abstract helper method we're using for the sake of this example that will give us the actual value of the counter, which would be 0 for the first run, and then a witness that points to that counter in the Merkle tree. So we have the value and the witness. Now we have to take the witness and hash representation of the real value to calculate the root hash of the tree and to calculate the key that the value belongs for according to the witness. If the counter commitment, again, the mistake here should be the computed counter commitment matches the counter commitment that's stored on chain. That means that the counter value that we have received as a private input right here is valid, and we can trust that value. We have to do the same for the key and the computed key to make sure that the witness was really for the key that we are actually meant to be using. So that's the public key provided by the user. That's how do you validate data coming from a tree into your smart contract. And in the second part, we will take a look at how do you write data to the tree. So let's move on. Updating the tree data. So this is a continuation of the increment method. So we will take the original counter value, incremented by the number that we have provided by the user. That will give us the new counter. And then we will use the same witness to compute a new root using the new value, right? So before we used the old value that was supposed to be in the tree that gave us the same root hash, so we could verify the integrity of the data. And if you want to upgrade, if you want to write to the same leaf, we will just use the same witness, calculate the new root hash using the new value that's supposed to be in the tree. And then we will take the new calculated commitment and we will set it as on-chain state. Rafael, do we have any questions in the meantime? You can start it basically anywhere you want. So one of the first things that I've tried to build in the ecosystem was an off-chain storage library. We will go through explaining why that might be difficult or not possible to use off-chain storage libraries in the next slides. Okay, so let's move on. Any other questions? I assume not. Okay, so let's build on top of what Steven was asking, and let's take a look at the design limitations of this approach of using Merkle trees for data together with smart contracts. So we know that users will execute smart contracts on the client side, independently of other clients. We know that this leads to preconditions pointing to the root hash of the tree. We've discussed it just now. And this means that if there are two users transferring at the same time, their preconditions will be the same. Their preconditions will be identical. So this means that when the chain, the L1, goes to process these two user transactions, one will invalidate the other. So the first one that succeeds will update the on-chain state. And when the second one is being processed, it will have a stale precondition pointing to the old on-chain state. So this makes it pretty impossible to achieve any meaningful concurrency if you write your smart contracts in the way that we have seen in the examples so far. We just discussed this, how the second transaction is invalidated, and we also have a diagram that shows you how this actually happens, right? So we have, this all happens on the client. We have Alice that is executing counters.increment. Then the increment method pulls in the actual data and the witness from some form of an off-chain storage. Could be an API, could be some distributed network, like we wrote libraries before for that, before we started writing Protokit. So we have some experience there. This produces, again, account updates, and the account update will try to update the chain state to a new root hash, and it will also have a precondition to the current on-chain root hash commitment. And the red part, the current root hash commitment, will match the current tree state. But after the first transaction is created, and if you have two in parallel, the first one will set it to the new root hash. Therefore, the second transaction precondition will no longer be valid, making the transaction fails, creating concurrency issues. So that was like the TLDR on ZK program and smart contracts. I hope you guys went from zero to ZK hero in the short span of time. And now we can move forward with the actual subject of the workshop, which is trying to build a private airdrop on Mina. So what is a private airdrop, and what kind of architecture do we need to build one? So we will be storing all addresses eligible. We have a question, yes? Yeah, we will touch upon that after the airdrop example. So let's go through the airdrop example, then explain how actions or sequence state could help you with that, and what kind of bottlenecks would you run into using actions and sequence state, and then what else can we do to solve these things, right? So, okay, going back to the architecture, we will store all the addresses eligible for our airdrop in a Merkle tree. So we've just seen how to work with Merkle trees, how to read and write data to them. Then, one important thing, very important actually, to keep this as private as possible, is that everybody will receive the same amount of tokens from the airdrop. If that wasn't the case, then we would basically create a link between an address receiving a certain amount, that information being public, and then when the claiming happens, you would be able to pinpoint which address received the tokens based on the amount to the original address that was eligible. So we want to avoid that, therefore everybody gets the same amount. We will also need to build an airdrop smart contract, which will have a claim method that will only give you tokens from the airdrop if you can prove that your address is part of the airdrop Merkle tree. We will also have to utilize something called the nullifiers to make sure that you don't claim twice by proving 2 times in a row that your address is part of the airdrop Merkle tree. We could just store the addresses that have already claimed in a separate Merkle tree, but that would defeat the privacy purpose of the private airdrop. Therefore, we use a nullifier, which cannot be backtracked to the original address that was claiming from the airdrop. So this effectively allows us to break the link between the address that was eligible and then the address that received the airdrop tokens in the end. So just a little bit of a disclaimer, this architecture is pretty similar to Tornado Cash. So it's something that you definitely shouldn't be doing because of money laundering concerns, stuff like that. I also have to say that we have limited time in the room and we will have to move to a separate room in about 10 minutes. So I will share another link in a moment. Okay, so moving on. We have this architecture. We want to build a private airdrop. So how would the smart contract look like? We would define an airdrop smart contract. It would store two fields on the chain. It would store the airdrop tree commitment, which is a Merkle tree that contains all the address eligible for the airdrop. Then it would also store a root hash of the nullifier tree, which contains all the nullifiers that have already been used to claim from the airdrop. Then we need a single method called claim that accepts several parameters. So it accepts the airdrop witness. That's a witness that allows us to calculate that a certain address is really part of the airdrop tree. Then the nullifier, which has been signed and created outside of the contract using the Mina signer. And then the nullifier witness, which will allow us to prove that the nullifier has not yet been used as part of the nullifier tree. So we first have to get the on-chain state and create the preconditions. So we do that in the first two lines by using this fancy method called get and assert equals, which allows us to save some space. And then we have to check if the user is part of the airdrop. So we have to take the airdrop witness that we have for a specific key, which would be your index in the airdrop tree commitment, and we compute a root and key using the value boolean true, right? So if you are in the tree, the leaf that's represented by your address will have a value 1, which is the field representation of the boolean. If it would have the value 0, it means you are not in the tree. So we compute the root hash and we also compute the key. Now we have to do two things. So before we talk about verifying the nullifier, let's talk about verifying these two variables. So we have the airdrop tree commitment, which is the on-chain state coming from here. And we have to assert that it equals the computed airdrop tree commitment. If we do this, it makes sure that whatever address used to generate this witness was actually in the tree because you managed to arrive at the same root hash as is stored on chain. Hope that makes sense. If not, we can try to explain it more, but just let me know in the questions. Then we also have to check the computed airdrop key and make sure that it asserts or it is equal. We have to assert that it is equal to the public key used to generate the nullifier, right? So we take the nullifier, we get the public key out of the nullifier, we turn it to field, we hash it, and we make sure that the witness is a witness for a key, and that key is the public key that was used to generate the nullifier. So we have all of these links, basically attesting that we can, like, it's basically a link in the proof or in the circuit that these variables are arriving at the correct, like the variables and the computation arrives at the correct values. So moving on forward with the logic. So the second part of the smart contract would be ensuring that the nullifier has not been used yet, and then adding the nullifier to the tree of nullifiers to make sure that it cannot be double spent again, right? So we have to update the nullifier tree. So what can you do here? So you take the nullifier witness, which points to the nullifier that you are currently using. We compute the root and key using the field 0. So we are checking that the nullifier is not in the tree yet. We get the computed nullifier tree commitment, which we will again compare with the on-chain state to make sure that the tree which we are proving against is the same as the tree or the state that is committed on-chain. Then we also have to take the nullifier key, which is the unique message that can be like stored publicly and won't allow anyone to trace the key back to your actual address that you used to create a nullifier. And we assert that it equals the computed nullifier key. So we use the nullifier key as the index in the nullifier's tree. So this 3 lines of code allowed us to check that the nullifier has not been used yet. And now what we have to do is we have to write the nullifier to the tree, and that's the last piece of the code in the contract. So we take the same nullifier witness and we compute a new root using boolean true. We should have used field 1 or boolean false here as well to keep it consistent, but at the end of the day, it's the same result. So we use the nullifier key and its nullifier witness to write boolean true to the leaf that is identified by the nullifier key, and it gives us a new tree commitment. So effectively, like, I know I'm talking a lot about commitments, computing a root, checking a key, or this or that, but effectively it's just key value storage. And you always have to take your data type, turn it into a single field, and then save that into the tree and store the actual value separately. So in reality, it's pretty straightforward, but you have to do all of this fancy math to verify the integrity of the data and to prove the update of the tree data as well. So we have the updated nullifier tree commitment, and we can store it on chain using the account update state. And then once we've done all of this, and the proof didn't fail because the nullifier has not been used yet, and the airdrop inclusion was proven as well, we can then use the send API of the smart contract to send Mina to the sender of the transaction and give him a fixed amount. The important part here is that the address that will be used in the airdrop witness and to sign the nullifier or to generate the nullifier will be different from the sender. And this will allow us to send the tokens to the sender address without creating a link to the original address that was eligible for the airdrop in the first place. So yeah, that's it for smart contracts. Before we move on, any additional questions, Rafael? Yeah, so Gregor is saying that the nullifier has convenience methods for all of this stuff. That is true. The reason why I wrote the contracts like this is because I'm not familiar with them in the first place. And the second place is because later down in the workshop, we will go through extracting this into a separate proof. So before we move on, I'm going to ask everybody to hop into a separate, into a different meeting room because we are running out of time in this one. And I will wait a couple of minutes after posting this link for you to join the second meeting room. All right, see you there. So we have gone through the part of the workshop where we explain what a proof is, what a circuit is, how you can use circuits to create smart contracts that can have their execution proven off chain. We've seen a diagram how that relates to Mina as an L1 and how it is possible to verify this off-chain computation of these smart contracts. And wait, one moment. I think I have a mix-up in my slides. Okay, wait. Is this being recorded? Yes, it is being recorded, and we will update the recording afterwards. Wait. So we've been through the design limitations, we've been through the airdrop. Okay, so let me just resume my screen sharing. Okay, we're back. So I think it's now time to answer Brandon's question. So how do we, like, is there any building way on the L1 to address the concurrency issues that we have been describing? Yes, there is. But before we talk about how you can address this, I want to talk about like the general approach. So the approach that we believe everyone should be taking to address these concurrency issues, and also the approach that the official docs of Mina are suggesting, is effectively to write your own rollups, right? So what would a rollup actually be? It would be that instead of users running their smart contracts off-chain themselves, the users would be effectively sending transactions, or referred to as actions in the L1 protocol, and then someone would roll all of these actions up, which would effectively create like a rollup block. So the L1 already has like primitives for like these micro rollups called sequence state, actions, and the reducer API. So the next chapter, we will talk about Protokit. Protokit is a framework that allows you to use the same concepts as sequence state, actions, and a reducer. And it provides you a very convenient API to write your circuits so that they can be rolled up using an approach like sequence state and the reducer. So we have these concurrency issues. We've seen the smart contract and how it can be implemented. Now we need to learn how to implement circuits in a way that we can roll them up into individual blocks and get them settled on the L1. So time to talk about Protokit, the creme de la creme of the workshop. So Protokit is a protocol development framework for privacy-enabled application chains, also referred to as ZK rollups or ZK validiums, or like depends on how you deploy them. To get started with Protokit, you just have to run the simple command below here. We won't do that now. We'll walk through the workshop, and then we'll do a live coding session afterwards. So what is Protokit? Protokit is a TypeScript-based framework for building ZK chains, ZK rollups, application chains, you name it. It's not another ZK EVM-based ZK rollup. Instead, it uses a custom-tailored ZK VM that is like privacy-friendly. Sorry. It offers a hybrid execution model that allows both off and on-chain execution. Off-chain execution means the same as we've seen with smart contracts before. It allows you to consume client-side zero-knowledge proofs, same way as the smart contracts on the L1. Chains running with the Protokit framework also get the direct benefit of end-to-end proven execution. So it means when your sequencer or the node operator runs your chain and processes user transactions, the sequence operator does not have any room for any malicious activity, because to produce a valid block proof at the end, he has to execute all the circuits that create your chain correctly with no room for anything malicious. Also, everything that you build with Protokit is going to be completely customizable and modular. So it means that if you don't like a certain part of the system, you can replace it very, very easily. One of the main design goals of the framework was to have a virtually no learning curve, but you should still be paying attention because there's going to be a lot of interesting stuff. So what I mean by no learning curve can be expressed very simply. So a lot of the APIs are similar to the smart contract APIs, and it's using the same O1JS DSL. So it means that if you've been using circuits or smart contracts before, transitioning to Protokit and getting rid of the concurrency issues by writing recursive rollups instead of just simple smart contracts should be fairly simple. So we want to build you want to build your own ZK rollup, right? You have your smart contract, you have your concurrency issues, and you want to address those somehow. So you can build a recursive ZK rollup that's going to be a series of recursive circuits that prove that transaction, or as Brandon was asking, action, execution, and the state transitions behind these, behind the business logic that's being executed. So a state transition is effectively Merkle tree operations. So we already know that the L1 offers sequence state and actions to help you build ZK rollups, but you still have to write your own circuits. And even if L1 didn't offer sequence state and actions as part of the protocol, you would still have to write your own mempool. So I will just detour a little bit to explain how this works. So with Protokit, we are not using sequence state and actions directly, but we are using the same identical concepts behind sequence state and actions, which ensure basically end-to-end proven execution of all of your actions without any break in the system. So it means that if a user dispatches an action and then there's a bundle of actions, that means there are at least 10 transactions that have to be executed. When the sequencer goes and executes the bundle of the transactions, the sequencer cannot skip transactions at their own will, which is the same concept as sequence state effectively is. Another reason for us to go with the private mempool over sequence state and actions is that just to dispatch an action as part of the sequence state on the L1, you would still have to create a proof. Don't quote me on that. Like, we have Gregor and Brandon here who can tell us more about it. But in my experience, or in my understanding, just to dispatch an action, you have to create a proof, which is much more time and resource intensive than just signing a transaction as you would in our private mempool. It still doesn't mean that you cannot use sequence states and actions. If you want, you can write a mempool backend or a mempool module for Protokit that would use sequence state and actions directly, and you wouldn't have to use our private signature-based mempool anymore. Okay, so Protokit enables you to build zero-knowledge, interoperable, and privacy-preserving application chains with a minimal learning curve, right? You already know that. So you can roll your own ZK rollup in a few lines of code. And it's also important to mention that these ZK rollups are effectively nothing more than a superset of ZK apps. So it means that you get the opt-in privacy features with public on-chain execution that allows you to deliver the best possible experience. So with smart contracts, the privacy is pretty much always there, let's say, and you don't have any room for on-chain execution. So there's no on-chain execution in the L1 smart contract, but with the Protokit chain, you get both. You get both the off-chain execution with privacy and on-chain public execution. This allows us to combine the business logic in a way that makes the most sense to get the most out of the user experience. So what is a Protokit ZK rollup or application chain made of? It consists of runtime, which is a series of circuits that define your application logic. These could be auctions, dexes, balances, vesting modules, or whatever else that your application might require in terms of business logic. Then we have the protocol circuits. So that's the underlying virtual machine, the block production, transaction fees are handled here, account state, stuff like nonces, all of that is handled under the protocol. And then we have the sequencer, which is like the node or the server that has offers mempool services and orchestrates all the block production and handles, most importantly, also the settlement to the L1. So once transactions are processed, block proofs are created, they have to be settled to the L1, but we'll have a diagram explaining that in more detail. So yeah, also the L1 settlement contract. Okay, what kind of features can you expect if you use Protokit? So main focus, having a supercharged developer experience. You just have to know TypeScript and a little bit of O1.js here and there. You can write and use reusable modules. You can use open source libraries that offer Protokit modules. Like, for example, we wrote a DEX. That DEX is open source, so you can take the balances module, which is effectively the ledger for the chain, from our DEX and use it as part of your project with no limitations. Also, the chains built with Protokit will have no data race conditions unless you choose to specifically engineer your system in a way that would recreate the issue with preconditions known from the L1, right? So if you want, you can choose to do that, since this is just a superset of ZK apps. But the main purpose of the tool was to allow you to build in a way that will not have race conditions. The on-chain storage that we will see in a moment is effectively bottomless because we use the largest Merkle tree possible, and the amount of records that you can store there is not even worth mentioning, because before you run out of available records, you will probably run out of memory anyways, or like the number is infinitely huge. So you still get your off-chain privacy because you can create proofs from circuits on the client side, same as with ZK apps, and send these as arguments for on-chain transactions to be executed in a sequence manner on-chain. You get to focus on your business logic. You don't have to do all the heavy lifting. So the operations that you have seen, for example, to verify data or to roll your own rollups, you wouldn't have to do that anymore because we wrote all the circuits and all the machinery behind the scenes. All you have to do is just focus on your business logic and write your runtime. Protokit chains or Protokit transactions are compatible with user wallets in the ecosystem because we rely on features from the Mina signer directly. As we said before, it's not another ZK VM, but it's a succinct ZK VM, and I hope I pronounced it correctly. I've been saying this for a while now, but you can re-implement the ZK apps preconditions in your runtime if you want to. But out of the box, you can just treat Protokit chains like you would treat development on another, like on any other EVM-like ecosystem that you're already familiar with. So this also makes it super easier for newcomers to build because they don't have to learn how smart contracts or zk apps work because they are super specific to the L1. And instead, they can reuse their existing knowledge from EVM-like ecosystems to start building with Protokit. Since this is a superset of zk apps, and you need some specific features that are not yet available in the zk apps on the L1, you can completely customize the behavior of your own chain. Therefore, you can get access to features faster than, let's say, the L1 would be able to iterate on, because the L1 bears a lot more responsibility towards the whole ecosystem, and features specific to your app might not be necessary for everybody else, and therefore belong on your app only. So you can do that with Protokit. Features that will be available soon. So the chains need to be interoperable with each other and also with the L1, with like varying degrees of security guarantees compared to the UX available. And you also need data availability unless you want to stay a Validium instead of a rollup. So we have plans to address all of these, but don't tell anyone just yet. So moving on, how does the Protokit architecture look like, or what is the life cycle of a transaction? So before we had the same diagram for smart contracts, and now we'll take a look at how to basically achieve the same things as before, but with Protokit. So the only thing that needs to happen on the client side is that Alice needs to sign a transaction. She doesn't need to prove anything on the client, which makes it basically faster, right? So we've discussed before that even if you want to use sequence state and actions, you still have to prove the change to the sequence state. So Alice creates a transaction specifying which runtime module and method and what arguments she wants to use, that is signed and sent to the ZK rollup or to the sequencer. So it's just a simple transaction. Then the sequencer takes all the transactions and executes them by running the runtime method, which means that it creates a proof of the runtime method execution. That also produces state transitions, similar to account updates that we have seen before. And then these state transitions are applied by the protocol. So the protocol writes the Merkle tree data updates, and then the block proof takes together the proof of the runtime execution and the proof of applying all the state transitions, merges them together, and creates a block proof. This happens for all the transactions until we have a final block proof. That block proof is then settled on the Mina L1. So every Protokit chain will have a smart contract running on the L1, which will receive block proofs only from your rollup, which means that you can settle to the Mina L1. So like, what does settlement mean? Like, you could run it without the L1, that would be like a sovereign rollup. That unfortunately doesn't have much security because you have like a centralized sequencer under the current model. And the only thing that you can rely on in this case with a ZK sourcing rollup would be that the execution would be correct, right? Because there's a circuit and everyone can verify the block proof. This is effectively how the Mina L1 works. Plus, you also have consensus, which makes it like a full proper L1. So since your ZK rollup doesn't have consensus, you need settlement instead. And you reuse the consensus of the L1 to settle your block proofs right here. So there's a block proof created that tells the chain that we are transitioning from state A to state B on the rollup, and that is sent to the L1. Do we have any questions in the meantime, Rafael? All right, let's move on. Okay, so before we were writing smart contracts and circuits. In Protokit, you won't write smart contracts anymore. You will write runtime modules, which will be the bread and butter of your chain. So users cannot just deploy smart contracts on their own to your chain. Your chain is built for a specific purpose, a specific application, and therefore the business logic is baked into the core runtime of the chain itself. So let's take a look at an example of how you could write a runtime to handle balances and native and third-party token transfers in your chain. So you would write a class called balances that would extend the provided class runtime module. Don't worry about the unknown. This is a config-related thing, and since we are not using any config for the runtime, we're just going to leave it empty as is. You also have to decorate it with a runtime module decorator that does a bunch of like interesting things behind the scenes that we might explain at another workshop. Then, same as on the smart contracts, you have to define some state, with the difference that a Protokit runtime is not limited to 8 fields. So, and you can also use key value storage. We call that a map. So we want to store a map of balances. There's going to be a state map where the key is going to be a public key of the user, and the balance is going to be a UN64. Then we need to define methods that users can call in transactions. We will label them with the runtime method decorator, and we'll just call this function transfer. What is important to note here, if you remember the previous diagram, this function is going to be triggered by a user signing a transaction and execute it on the sequencer. So there's not going to be any concurrency issues because the sequencer will order all the user transactions and execute them and the state transitions in an ordered or a sequenced manner. So what does the transfer method do? It transfers from a public key to a public key a certain amount. So how would the implementation look like? So first we have to obtain the from and the to balance. We just do that using the state map get API, which is relatively straightforward. Any calls to the state API will produce state transitions behind the scenes, which are like quasi equivalent to the account updates. Then we have to check like some pseudo transfer logic. We have to check if the from balance of the from key, the from balance is greater or equal than the amount being sent. We check that here. This gives us a boolean from balance is sufficient. One important thing here is to note that we cannot use assert APIs from O1.js because we don't want this on-chain execution to fail forcefully. We want to fail it in like a silent manner that can be then processed by the protocol. So we use a custom assert API that's available from Protokit. So you assert that the from balance is sufficient, and if it's not, you will throw an error that the balance is insufficient. This creates a flag behind the scene that tells the protocol that the method was not executed correctly and the state transitions for it should be discarded. But the transaction will still be included in the block, but the status will be that it failed. This is something that we've seen, for example, Starknet only had recently, or Starkware, I don't know. Like they were not able to even process failed transactions before. So then we have to decrease the balance from by the amount that is being sent, and we have to set it to the chain API. There's a little error here. Let me just fix that real quick. So when you are setting the balance, you have to set it for an address and then a value. So it would actually look like this. Yes, questions? Rafael, do we have any questions? Sure. Let me do it just really quickly. So we use a dependency injection framework called thisrange to orchestrate the chain and the dependencies and all the modules that come with it. Runtime module makes the class injectable as part of the dependency injection framework. That's like the main feature that it does. The state decorator, I'm not sure if you asked about that, but so the state decorator basically helps us identify which index in the global Merkle tree state the balances are stored under. So if you store a balance for the from public key, the path or the index would be created from balances dot the from address, and that is what we would compute the leaf index in the global tree state from. Hope that makes sense. And then the runtime method is probably the most verbose, like internally verbose part of code in the entire system. If we think about like the module API itself, and what it actually does, it wraps your function into another function that ensures that the protocol execution was correct. So you can imagine your function being nested into another parent or a higher order function that also checks your execution status, extracts all the state transitions, creates the public outputs for the underlying ZK circuits, and all the other things that you don't want to care about as a developer unless you really want to go down to that level like of the tooling itself. So this is pretty much a heavy lift from the shoulders of the users so that they can focus on only writing the piece of logic that matters to them, and they don't have to care about the protocol behind the scenes. Is there any other questions, Rafael? Yeah, I mean, we don't have that much time. I don't know how long people want to stay. TLDR, you get on-chain execution. You don't get that with smart contracts. That's like the main selling point from the slides before. All right, let's move on. So writing your own runtime. So now you wrote a runtime module. Now, how the hell do you create a rollup out of it? How the hell do you create an app chain out of it? So writing your runtime, now testing your runtime, right? So if you want to execute a runtime, let's first do a little bit of a setup. So we first create some keys for Alice and Bob so that we can do the transfer from and to. Then we create a testing app chain from runtime modules. And the only thing we have to do is pass in the balances class that we have created with a config that's empty because we are currently not providing any config for that module. So now we have an app chain and we can start it. Very simple, one line of code. And we also can set a signer for the app chain API, which will be Alice. This will be obvious in the next slide, where we have to create a transaction to the transfer method of the balances runtime module. We first do that by extracting or resolving the balances runtime module. This gives us an instance of the balances runtime module. Then we make a transaction using the appchain.transaction API, using Alice as the sender, and we make a transfer using balances.transfer from Alice to Bob for a certain amount of tokens. We have to sign the transaction and send it. And then in the test, what you would have to do is to produce a block. This basically triggers the block production pipeline in your tests as part of your testing app chain, processes the transactions that you have signed and sent, processes all of the state transitions, and gives you a block proof, even though it's just a simulated block proof because in your tests you are not running it in approver mode because it will be slow, etc., etc. So you eventually produce a block. Now, the last step would be to actually take a look at the on-chain state and make sure that Bob has really received the balance that we have transferred as part of our logic. So you can use the query API for that. So appchain.query, we are querying the runtime state, the balances module, the balances state map, and we are getting an entry from the key value of the state map identified by the Bob's public key. And if our transfer was successful and the block was produced correctly, the balance of Bob that we would receive would be an instance of UN64 data type holding 100, right? To be able to actually do this, you would have to mint the balance for Alice first, otherwise the transaction would fail. But like to keep things simple, we've only demonstrated how the transfer would work. All right, so the last part of the workshop, I believe we have about 50 minutes left, so we might not do like a live coding session, but I can walk you through how the airdrop code that we have seen for the smart contract would look like in a Protokit runtime, what kind of components would you have to build for that, and how the test would look like, and how the overall developer experience would be. So, assuming we don't have any other questions, Rafael, okay, so let me just stop sharing and prepare the workshop materials. Okay. So, I'm going to reshare my screen real quick. Enter screen, this one. Okay. So, I hope you can guys see my screen. Let me know if I should like zoom in or anything. Okay. So, I'm in my editor. You see the workshop repository. You have two folders, one for the workshop slides, I'll share the link to the repo later so you can check it out yourself. But the folder that we are after right now would be the one which tells us how to build the same private airdrop functionality as we've seen with the smart contract, but with the Protokit runtime. And what kind of benefits would we get if we build this using Protokit, and what kind of things would not work with the smart contract on its own. So the components that we will need for our runtime would be a balances runtime that allows us to mint a certain balance. So when the user claims for the airdrop, we will mint a balance for them. The only thing that it does is the same as the balances example we've seen just now. It gets the balance, increments it by the amount that's necessary, and it updates the user's balance. Keep in mind that mint is not tagged with the runtime method decorator. That makes it not publicly callable through a user transaction, and it makes it only callable internally from other runtime modules, which make sure that users are not minting freely as they see fit, but based on some business logic that needs to be applied beforehand. Then we will also have a airdrop runtime module that will do a bunch of different things. So it will store a commitment to the airdrop tree, the same as we had in the smart contract. But this time, it will not store a commitment to a nullifier tree. Instead, it will store a key value state map of nullifiers and an indicator if they have been used or not. So the airdrop runtime module will do also one interesting thing, and that's create a dependency to the balances module. So if your testing app chain would have a runtime consisting of balances and airdrop, it would enable the airdrop runtime module to inject the balances module and use it directly. So we do that by the constructor, and that is why we have the runtime module decorator, so we can use the dependency injection library and so on and so forth. So going through the methods, like the first one that we would implement would be set commitment. What this does, it tells the airdrop runtime which commitment or which airdrop tree root hash to use. So let's imagine that we wrote this class, we wrote the on-chain state for the commitment, and then we wrote the method for setting the commitment. Now, we would have to write a test for it, right? So let's move back to the test and see how a test for this would look like. We don't need this, and we only need these two. Okay, so before all of the tests will run, we will have to again set up the testing app chain that will consist of the two runtime modules that we have built and an empty config. Then we will set Alice as a signer, start the app chain, and resolve the runtime modules so that we can use them within our tests and within our transactions. So the first thing you have to do is set the commitment to the airdrop tree root hash. So to do that, we have to also define the airdrop tree. We do that above in the test. We create a new Merkle map. We create a new key using the Alice's address, and we update the Merkle map. This is what Steven was asking before, like where do you store the Merkle tree? For the purpose of the test, it lives only in the memory here. Keep in mind that this is the airdrop tree that is not part of the on-chain state. We just use the commitment from it. So we now have a map where Alice is stored, and that indicates that Alice is eligible for the airdrop. And we also obtain a witness from that that's useful for later. So to set the commitment, we get the root hash out of the map where Alice is already stored, and we send the transaction, sign and send it, produce a block, and then in the test, we ensure that the commitment actually made it to the chain state by querying the runtime airdrop commitment state and running an expect that ensures that the on-chain commitment, on-chain meaning on the L2, matches the root hash from the map that we are using. So that will be the first test, right? Now we have a runtime that stores a commitment. So now we have to move on. We have to move on to the implementation of the claim method. So before in the smart contract, we provided all the witnesses, including the nullifier, to the smart contract method itself, because it was executed off-chain. However, runtime methods, as we already know, are executed on-chain by the sequencer, not on-chain on the L1, but on-chain on the L2. So we cannot tell the sequencer which address we are claiming for, because that would break the purpose of the private airdrop, and it would expose which address we are claiming for, which is the only thing that we are trying to avoid by design. So instead, to preserve the privacy aspects, the claim method will accept an airdrop proof. The airdrop proof will do the exact same thing of verifying the nullifier and the Merkle proofs of the airdrop tree of the chain on the client side in the browser. It's going to be signed and sent as part of the transaction to the sequencer. And then it's going to be executed by the sequencer when the claim method runs, and it's going to run all of these other additional business logic. So let's take a look at how the airdrop proof is constructed first before we take a look at what else does the claim method do. So our airdrop program is really simple. It results into an airdrop proof, and it has a single method called canClaim that has two private inputs, the Merkle map witness for the airdrop tree and the nullifier as before. As an output, it has airdrop public output, which is the root hash that we have been able to calculate from the airdrop tree witness. And it also has a nullifier key in the output so that we can then process the nullifier key on chain and store it in the state map of nullifiers in a sequenced way without having the same precondition issues as with the L1 smart contract. So this is pretty much the most important part, and it should be like the key takeaway in terms of the differences between smart contracts and runtime modules. The runtime modules allow you to overcome the concurrency issues and the race conditions by moving part of the execution on chain, where the state transitions that need to be sequential are done in a sequential manner by the sequencer. So we have the root and the nullifier key, and now let's take a look at the implementation of the ZK program. So we know the private inputs are the witness to the airdrop tree, and then the nullifier itself, and it returns the public output, which we have just discussed. So we take the nullifier, this happens off chain, and we take a look at the public key that was used to calculate the nullifier, and we turn it into fields, and we hash it again. This will create a single field, which will be the key used to calculate the root hash from the witness, right? So then we take the witness for the airdrop tree, we compute the root and key, expecting this address to have a bool tree value in the tree that gives us a root hash and a computed key. So we have to assert that the computed key from the witness, or the key that identifies the leaf that the witness is created for, is the same as the key derived from the nullifier's public key. So effectively what this does, even though I probably overcomplicated the explanation by a tenfold, is that it creates a link by the witness being for a specific leaf, which means being for a specific address, and the nullifier being for a specific address. This is very important. Additionally, it also verifies that the nullifier was created for a specific purpose. We do that by using a message that needs to be unique enough. Like for the test purposes, it's very simple. It's not unique at all. This would mean that as an application developer, you are meant to create a nullifier that's using a message that's unique enough so you can prevent collisions with other applications by using the same message, because then the nullifier could be misused or double spent for a different purpose, and you want to avoid that. So the message needs to be unique, not like in our test. We've computed the root, we verified the key, we verified the nullifier, and now what we can return from the proof is the computed root to make sure that the proof was done on top of the correct witness and using the correct Merkle tree data. And we also export the nullifier key so that we can break the link between the address used to calculate the Merkle proof and the address that claims the funds in the end. And we do that by connecting them basically by a nullifier, which is something that cannot be backtraced to the original address and will be stored by the nullifiers tree, this nullifier here. So this gives us an airdrop proof, and the airdrop proof has the public output of the root and the nullifier. So going back to the runtime and how does claiming work. So you provide the airdrop proof. This shouldn't be there, obviously, right? You verify the airdrop proof, because we know that verifying and another recursive proof is just another computation that needs to be verified. Then we get the commitment from the on-chain state. We make sure that we create a soft assertion, so we don't assert equals. We create this soft assertion and a soft failure potentially, that the airdrop proof and its public input and the root that it contains equals the commitment and therefore matches the same tree as is stored on chain. If it doesn't, you get this custom error. Now we need to check if the nullifier has already been used. So we take the nullifier key from the public output of the proof. We try to get it from the nullifier state map. And if we are able to assert that the value for the nullifier is false and not true, which means it hasn't been used, then we can continue. If at this point we figure out that this nullifier has already been used, we need to throw an error, and that's why we have this assertion here. So then if it wasn't used and the transaction didn't error out, we will set the nullifier key to the nullifier state map to make sure that it cannot be like reused again, which is what the logic above checks as well. If you run this the second time using the same airdrop proof, using the same nullifier, it would error out because the nullifier has already been used, and that's also possible without like having to keep track of who the original address was. So once you've completed all of these checks and you know that the user is eligible for the airdrop and his nullifier hasn't been used yet, you can mint the balance for the user. And we do that by minting the balance for the sender of the transaction, which is hopefully a different address if you want to preserve privacy than the address that you're approving for. And we will mint you 1,000 tokens. And that's pretty much it. Now we have to take a look at how it looks in the tests, and then we can use the rest of the time to discuss additional questions. So we've seen how setting the commitment works. This was this test. And now we have to see how to construct a proof, how to create a nullifier so that we can make the transaction here. So we first have to create a test nullifier using the O1JS API for a specific message signed by Alice. That's important. So we have a nullifier for Alice. Now we have to execute the can claim method of the circuit using the provided witness and the nullifier. And we have to turn it into a mock proof. So let's take a look at how that looks. So a mock proof is going to return us an airdrop proof, which is going to type check and be a valid proof for the airdrop program. So it's just like syntactic sugar for like testing purposes that we can use to calculate the dummy proof, and then return an instance of the proof class that would contain the correct public output that we are using for testing. So we don't actually have to run the proving, we just have a mock proof, and we can do the tests pretty fast. So we have the nullifier, we have the proof, now it's time to do the transaction. So we send this mock proof to the airdrop claim method, and we sign it and send it, then we again produce a block, and then we have to do some checks to see if the transaction was successful or not. First, we can check the transaction status to be true. That is what we're expecting to work. Then we can check if we have the stored nullifier and if it's true or not. If it was false, it means that the nullifier wouldn't be stored. Now the value of the nullifier is true under the nullifier key, so we know that the nullifier has been stored. And then we have to check the balance for Alice in this case, because we are sending it to the same address as is in the airdrop whitelist, which is not exactly what you want to be doing. You should be a separate address, right? But for testing purposes, it is the same address. So we check the balance of Alice by looking for the runtime balances state for Alice, and that is 1,000 because the airdrop runtime has transferred 1,000 tokens, or actually minted 1,000 tokens for us as a result of the successful airdrop claiming. And then we also have a test where we have a negative case where we try to claim using the same nullifier and the same airdrop proof, and this results into a failed transaction where the error is that the nullifier has already been used. The nullifier still stays true and the balance doesn't change. So that's pretty much it as far as the workshop goes. I believe we exhausted the time precisely. So if you have any questions, I would be more than happy to answer.